Now we talk about a very commonly used transformation of variable in the regression analysis. Okay, so typically for this particular form, we call it semi-logarithm form, in the sense that we take natural logarithm of the dependent variable. In this case, we take the natural logarithm of wage in the simple wage regression. Right? So before we have an equation wage equal to beta 0 plus beta 1 times education plus u. Now we have log, which is natural logarithm of wage, log wage equal to beta 0 plus beta 1 times education plus u. So if you are not familiar with this log, so let me simply explain it. So suppose you have a number, say 2, okay? You know that you can define a function which is called 2 to the power x, right? So if, say, for 2 to the 2 squared equal to 4 and 2 cubed equal to 8. So this operation has an inverse operation, which is called log operation. Right? If we have log, use 2 as base, 4, then equals 2. Okay, so log 2 of 8 equal to 3, and in general we have log 2 of 2 to the power x equal to x itself. Okay, so it basically means that if y equal to 2 to the power x, then log 2 of y equal to x. Right? So now we consider a very special number which is called the Euler number. It's approximately equal to 2.718. Okay? And it's an irrational number, so we know it's only roughly equal to this number. Okay? So it's similar to the logarithm with base 2. Logarithm with base e is called the natural logarithm. Okay, so it basically means that if y equal to e to the power x, then log, use e as a base, y equal to x. But usually we omit this this e. Okay, if the base of the log is this Euler number, okay, or exponential number, and this is the exponential function. So this is the natural log. Okay, so we simply write log y or log x. Okay, log y equal to x. This is the meaning of this log. Okay, if you don't know this. So why we would like to use log instead of wage itself? There are many reasons, but today later I will talk about more on these logs, but today let's just get familiar with simple and one of the most important thing that we use this log is that it changes the interpretation of the regression coefficients. Okay, in particular in this example, beta 1, if it's the original wage equation, wage equal to beta 0 plus beta 1 times education plus u. In that case, we know that the interpretation of beta 1 is that if years of education increased by 1 year, then wage, how much the hourly wage is increased, right? Or changed. But here, the meaning of beta 1 is that the percentage, okay? The percentage change of wage if years of education are increased by 1 year, okay? You don't need to understand the interim steps to arrive this, but remember the final meaning, the interpretation of the coefficients. That's the most important. If you run a regression, you need to know how to interpret your results, right? Basically, you need to, at the end of the day, you need to know two things: how to run the regression, how to interpret your results. Okay, that's the most important for this class. Other things I think is better that you know it. Okay, so it tells you why we use these estimates, why we use this method to run regression. Right? And typically, you need to decide uh, these things. But first of all, what's your data set, and what are the appropriate method to apply to your data set, right? What are the econometric model, the regression equation of your that you want to study, and what are the appropriate method to run the regression, okay? And how can you use software to run this regression and get estimates? And finally, you can reinterpret the results. That's the most important things. Okay. So this is the semi-logarithmic form. So here, what we do is we have data on wage and education, right? And we take natural logarithm of wage. We apply natural logarithm on the wage data, so we get this number, and then we run the regression by regressing log of wage on education. Then I put this into the computer, I get these two estimates, especially this beta 1 estimates. Okay? So it tells you that the wage increases by 8.3% for every additional year of education. Okay, the meaning of this beta 1 here. Okay. 0.083, which is 8.3%, right? And the graph, the relationship between education and wage is roughly looks like this way. Okay, it's looks like the exponential function. Okay? So it's kind of uh, convex. Okay? This is the semi-logarithmic form, and another uh, type of commonly used regression model is this logarithmic form. Okay? So we have both log of the dependent variable and the log of the independent variable. Again, by taking this form to do the regression, it also changes the interpretation of the regression coefficients. Now this beta 1 means that, for example, this is a CEO salary and firm sales regression equation. Okay, so the dependent variable is the natural logarithm of CEO salary, and the independent variable is the natural logarithm of the CEO's firm's sales. And the interpretation of this beta 1 is the percentage change of the salary. This percentage comes from this log of salary, okay? Percentage change of salary if the sales increase by 1%, okay? Not 1 unit, but 1%. This 1% is resulted from the logarithm transformation of sales. Okay? So basically, we can learn, we can come to this conclusion that if you see logarithmic change or logarithmic transformations, they are always percentage changes. Okay, if you observe change in logarithmic points, they are always percentage changes. Okay? So that's why this beta can be interpreted as percentage change of salary if sales increase by 1%. So in general, this beta means that the percentage change of the dependent variable y if the independent variable x increased by 1%. Right? And this is so-called in microeconomics, this type of relationship, this type of parameter is called elasticity. If you still remember, right? The demand elasticity, which is the percentage change of quantity demanded if the price increased by 1% or decreased by 1%. Right? So the supply elasticity, which means if the price increased by 1%, the percentage change of the supply, the quantity supplied. Right? So this is also called elasticity. Okay? So here, if again we have data on salary and the sales, and we take logs of salary and the logs of sales and run the regression by regressing log of salary on log of sales, we get these two estimates, and particularly we focus on this coefficient, which is which is 2.257. So it says if the sales is increased by 1%, then the salary of the CEO will increase by 0.257%. Okay, so which means that the elasticity of the CEO's salary elasticity to sales is 0.257. Okay, so this log-log form postulates that the relationship between salary and sales has a constant elasticity. Okay? It's beta 1 is the elasticity, but if you have this regression without logs, regress salary on sales, then you postulate that every unit of increase in sales will lead to a constant increase in salary, okay? Not the percentage point, okay? Not the percentage point. Okay, so this is about the logarithm transformation in the simple regression, and later we will discuss more, okay? Maybe after 2 or 3 classes.